An AI foundation model, no matter how advanced, is just raw intelligence. The system that actually binds it to reality is the harness. This harness surrounds the model. It constructs the prompts, manages the system state, invokes external tools, and coordinates the execution of tasks. As APIs update, operational environments shift, and user requirements expand, to prevent system failure, the harness must continuously adapt to these external changes. The process of adapting the system usually starts with a simple request from a human developer or a coding agent, describing a new behavior the software needs to perform. But before a single line of new code can be drafted, the developer or agent has to figure out exactly where in the current architecture that new behavior belongs. Ultimately, an autonomous agent's actual real-world capability is strictly limited by the agility of the code infrastructure that is running it. Identifying every code location that implements a target behavior is the mandatory first step of any system modification. Look at a standard production repository. The architecture is organized strictly by hierarchical files and isolated modules. Modification requests, however, are framed by what the system should do. This creates a direct collision, an impedance mismatch between behavioral intent and the rigid architecture. Production harnesses make this even harder. They are large and tightly coupled, meaning a single behavior is often distributed across multiple different modules. When an autonomous coding agent attempts a complex repository update, this failure to localize behavior is exactly where it stalls out completely. The difficulty of mapping human-readable intent to machine-organized files makes localization a primary bottleneck in agent evolution. The software industry typically relies on 3 tools to inspect codebases: code search, repository indexing, and long context processing. These tools operate by mechanically scanning the repository and returning raw text chunks based on semantic similarity to the search prompt. They return fragments of code, but they leave a complete void regarding how those isolated fragments actually interact to form a system behavior. Because of this gap, the actual mapping from behavior to code must still be reconstructed entirely by hand. Trying to brute force this manual reconstruction by dumping the entire repository into a long context window leads to severe token bloat and hallucinated edit plans. Dumping files into a massive context window fails because it provides raw data without operational context. To bridge this gap, the system requires a behavior-centric representation. This is the Harness Handbook. The handbook acts as an automated translation layer, mapping operational logic directly to the raw source codebase at the bottom layer. Construction begins with static analysis. A sweep of the codebase extracts the structural dependencies, raising them into a middle layer of logic. Next, an LLM-assisted structuring layer analyzes those dependencies and interprets them as distinct, high-level system actions. When these steps are complete, the layers lock together. Every distinct behavior in the system is now permanently linked to its exact source file. This architecture is dynamic. As the underlying repository changes, the handbook automatically resynthesizes itself. By programmatically compiling these behaviors, the human is removed from the loop of translating operational intent into machine architecture. Even with a complete structural map, an agent still has to navigate it without overwhelming its own processing constraints. Navigation is handled by an execution engine called Behavior-Guided Progressive Disclosure, or BGPD. BGPD executes a top-down targeting process. It begins its search at the highest level of behavioral nodes. From there, it systematically drops down through the layers. It isolates relevant sub-behaviors and filters out the irrelevant repository branches until it hits the specific code. Then, a mandatory verification step occurs. BGPD cross-references its candidate locations against the live source code to confirm the edit path. It functions as a high-precision targeting system, verifying the exact edit locations before a single line of new code is drafted. This architecture was rigorously evaluated using diverse modification requests against open-source agent harnesses. This chart displays performance results. Handbook-assisted planning improved behavior localization and edit plan quality while utilizing significantly fewer planner tokens. The performance gap was widest across 3 specific architectural pain points: scattered sites, rarely executed paths, and cross-module interactions. Standard retrieval models lack the structural tethers required to navigate these zones efficiently, making the behavior-to-code map a necessity. Evolving complex agentic systems depends entirely on determining exactly where an edit belongs, not just generating the edit itself. This prompts a question about the near future. What happens when AI systems no longer need humans to map their own architecture? Automating this mapping process provides a functional path for systems to independently navigate and modify their own codebases.